Hi everyone, welcome to the third session of the World Bank and iRAP Helping Save Lives in Africa, BIGRS 2020-25 webinar series. Today we'll present the iRAP model, and I am Alessandra Fransoia, the Training and Accreditation Coordinator at iRAP, and I will be your moderator today. Our housekeeping. Our webinar will have 90 minutes and we'll have time for questions. All attendees are muted, but you already know that you can post your questions on our chat and our presenters will stop after their presentations and I'll read your questions to them. And this session is being recorded and it will be available for you on Schoology after the presentation. We'll also post the PDF version of the presentation. So as you've had before with the other sessions, we have more materials there and I've been posting on the next day these files for you. So our webinar series has 4 parts. Today is our day 3 and we'll talk about the iRAP model. We have 3 presenters, Greg Smith, the Global Program Director at iRAP. Hi, Greg, how are you?
Hi, Ellie. Hi, everyone. Thanks for having me and thank you for joining.
Thank you. And Marco Sevrovic, the Senior Road Safety Engineer at iRAP.
Hi,
Marco.
Hi, Ellie.
Welcome.
Thank you for joining.
And Morgan Fletcher, the Senior Road Safety Engineer at iRAP. Hi, Morgan. How are you?
Hi, Ali. I'm very well, thank you. Thanks, everyone, for joining.
Thanks for joining us. And the agenda for today, we'll have a review of your assignments, the star rating of a road, and we'll give you the address to the Vida demo video. Greg will present the star ratings, and Morgan will present the star rating and investment plan. Marco will present the crash risk mapping, and Morgan will again present and conclude the webinar with the tracking performance over time. We'll also give you the assignment for this session. So just here, I'll give you a brief comment on your assignment, and I will have ask Greg also to support on this. A few people, we had many submissions, which was very good, and you all did very well. Just a few questions that we received in your submissions. So the instructions we ask you to, or how Greg showed how to use the demonstration, you can select the cross-section and also change the attributes according to what you see in the image. And we also gave you the standard categories that you need to use for your assignments. And the other thing that we saw is that you need to propose 3 countermeasures. The idea of this assignment is to show you that sometimes 3 simple countermeasures can improve safety of the road users. And try, when you propose these countermeasures, try to achieve at least 3 stars for all users. With this image, you can do that. We did the exercise, but I just want to say well done to all of you. There is no passing or failing. The idea is for you to practice and see how it works. Greg, do you want to comment anything on this assignment?
No, Ali, I think you covered it all well. And like you said, the main purpose of this particular assignment is for you to go into the demonstrator and try it yourself and give it a go. So we're not marking this about whether it's right or wrong. But like Ali said, you can remember to take that chance on the little tabs that are on the demonstrator, the mid-block, intersection, flow, speed, and so forth. Within those, you can change the design of the road and see what the impact is on the star ratings. So yeah, if you haven't had a chance to do that assignment, do go in and give it a try. And if you have any questions you would like to post in the system, please do that.
Thank you. And also, Greg made a video explaining the part that he wasn't able to present last week. So this is the link. I also posted on Schoology on the part 2 folder. So it's there for you. Very interesting video, Greg. Well done. I think it was in a good way that didn't work there, because I think we have a very complete, you can use this video in any situation if you want to know more about VIDA. And it's saved for you also the link on Schoology. And now
okay. Oh, sorry, I would just add, Ali, before we jump on, that what actually happened, if you were in the webinar in number 2, what happened was VIDA just froze, and it was a fairly terrifying moment for me while I was presenting. But what actually happened is, while I was presenting, a lot of people logged in to try and use VIDA during the webinar, and we had in the webinar hundreds and hundreds of people. So a lot of people obviously jumped into VIDA to take a look. On top of, there was already a lot of processing going on around the world from other projects as well. So the system just got overloaded. So I'm very sorry for everyone who was in that webinar who didn't get to see it finish, but hopefully this video tells you everything that you need to know. And like Ali said, it's available now on YouTube, and you can watch it whenever you like.
And Greg, while you are here, I'll hand over to you to present the overview and star ratings. Greg Smith, the Global Program Director at iRAP. Greg, the screen and mic are yours.
Thanks, Ali. So yeah, what I'm going to do, if you go to the next slide, Ali, is talk about the iRAP methodology, quick introduction, but I'm going to particularly focus on the star ratings component of the model. This presentation is going to be reasonably quick, so you're not going to be a master of the iRAP methodology, but hopefully you'll see some of the key components and learn enough that you know have some interesting questions that you can ask us afterwards. So about the iRAP methodology, it was developed, I want to say about 15 years ago originally, and it's really designed to help accelerate the uptake of safer road infrastructure all around the world. The methodology is free, so you can go onto the iRAP website and grab information about the methodology, the specifications, all for free in PDF documents. I'll show you the links to those in a moment. It includes what we call proactive and reactive protocols. I'm going to leave it to colleague Marco to talk about that in a moment. It's data and evidence driven. So it's very much focused on collecting data about the road or the design, using evidence about risk factors that are published in the literature, and putting together scores for the roads. It's globally standardized, so it's the same model that's getting used all around the world. And what that means is it becomes very repeatable. Someone doing an assessment in Ghana is using the same methodology that's doing an assessment in Croatia, for example. It's very adaptable. It applies to all the road users. It can be used at a single location or across an entire road network. And it can be applied at any stage of a road's life cycle. It can be done at the network level for an existing road network as part of planning. It can be done in the design phase, whether it's feasibility or detailed design. It can be done pre-construction, post-construction, and during operation over a number of years. The metrics that get produced, which we're going to talk about a little more here, the key star ratings and fatality estimations are some of the key ones. And again, because they're metrics, they can be used to set targets for designs and road networks. And in fact, the Global Road Safety Performance Targets number 3 and 4, which have been adopted by the UN and offered to countries voluntarily to take those up, both include reference to the iRAP star ratings within those. Also supported by VIDA, a central online platform, which 99.9% of the time works really, really well. And it's also supported by a global accreditation scheme, which Ali is going to talk about a little in the next webinar. It's governed by the Global Technical Committee. So if you go to our website, irap.org, you can take a look at the Global Technical Committee and find out who's on that and what they do. And key reference documents, particularly for this presentation that I'm going to do, are contained at iRAP.org methodology and specifications. So I'll hand over to Marco. He's going to talk a little about the concept of proactive versus reactive protocols.
Thank you, Greg. Yeah. With this nice example, which is not actually related to road safety, I'll try to explain the safety principle in general, the safe system in general, which is the core behind the iRAP protocols and iRAP methodology. So if we have a nice infrastructure feature as shown in this image, it's a balcony which is used by humans, it's used by people, and of course we know that it doesn't look safe at first, because as humans we are well aware of what might happen if we step over the edge of this balcony. And we are well aware, but imagine if you had balconies like this built in, and you just say that for the people, you don't cross the edge, or simply we just put a white line here, like a road marking, and say do not cross. Can you imagine that accidents would happen at these locations? They probably would, because people usually don't make fatal mistakes on purpose. They do it because they are not aware, they are not paying enough attention, and they just make a mistake. So we typically, as humans, we make mistakes every day with our movements, with our decisions, and whatever we do. So if we know the solution for this problem, it's basically putting a safety barrier here, or a guardrail, or a fence, or whatever you like to call it. And this is a simple and feasible solution, which is actually mandatory in many countries. You cannot have people living in a building like that if you don't have a guardrail on this balcony. So if we move to the next slide, what if we multiply the problem? If we multiply the problem and we have a whole building with balconies like this, a traditional reactive approach would mean that if we have a person that falls down from one balcony, we put a point here, said, okay, this is a dangerous balcony. Next click. And then we wait. And we do install a guardrail, and we say, okay, this was a problem. We put a guardrail on this one. And then again, a few days after, a few months after, we have another person fall down from another balcony. And again, our engineering solution is to put a guardrail there. Click. And then we wait again. And then we have another person falling down. Next click. And then again, we do the same procedure. We put the guardrail. This is basically the clustering analysis. This is the analysis of road accidents. This is what we are doing in many countries. We are looking at locations where people are getting killed and then fixing the problem after somebody got killed. So this principle, if applied to this building, as you can see, would be quite problematic. Proactive approach is actually to install guardrail on all of those locations, as the next clip show. Of course, the problem we have here is we sometimes in road transport, we don't have the money to actually install guardrails on all locations and to make all roads completely safe. So that's why we actually have to combine both the reactive and the proactive methodology. So coming back to Greg with the proactive approach, we will explain the principles, and then later on Morgan and I will show you how we can combine the two together to getting to the road safety targets that we set. Greg?
Thanks, Marco. Excellent example. So I talked about the iRAP methodology, and it really includes 4 key protocols. First one is star ratings, then safer roads investment plans, which includes the component for fatality estimation function, the crash rate risk maps, and then performance tracking. So in the presentation tonight, we're going to touch on each of one of these 4. So I'm going to begin with the star ratings. So just to reinforce, the key resources that I'm referring to in this presentation are listed on the screen. So these are just regular URLs that you'll be able to click on. So they'll be saved in this presentation, then you can take a look at them afterwards as well. So about the star rating model, like Marco said, it's a proactive model. It's one where we can produce some meaningful information about the risk of being killed or seriously injured on a road without waiting for crashes to occur on that road. We basically look at the design of the road and we apply data and evidence and make a score about the risk that someone faces. It produces risk scores for vehicle occupants, motorcyclists, pedestrians, and bicyclists. And the star ratings, they represent the risk of death and serious injury to an individual road user. So it represents the risk, for example, of an individual pedestrian crossing the road or an individual person in a vehicle driving along a road. 1 star is the highest risk and 5 stars is the lowest risk. The general procedure for producing star ratings and the investment plans which connect to them are shown in a simple way on this diagram. It begins with data collection, and that's usually a road survey. What we need is some sort of imagery of the road. We need to see what the road looks like. That can be a series of photographs, or it can be a video, or it could be, for example, Google Street View imagery. We then do what we call road attribute coding. So every 100 meters along the road, we will record the road attributes that are in the model and which we know influence the risk of crashes happening and the severity of the ones that do happen. So that happens every 100 meters along the road. The data is then prepared. We put it together with some other data like traffic flow and speed data. That then goes into the VIDA online software, which we presented in the last webinar, where the star ratings are produced, and that then enables an investment plan to be created. So Morgan's going to present a little on investment plans in a moment. And you can see it loops back there to say road design. So also it's an important point that these star ratings and assessments can be done for designs. And the demonstration that I did in VIDA in the video that we talked about earlier is in fact for a design. It's not for an existing road. So it can be done for existing roads and designs off AutoCAD drawings or paper drawings. The model, and so getting into how the model was built, the model is built around some key crash types that we know account for a large percentage of the deaths and serious injuries that happen all around the world. So in this table, you can see the 4 different road users listed across the top, and the types of crashes that are considered in the model is where the green ticks are. So for vehicle occupants, the model actually looks at the risk of running off the road on the driver's side. So if you're in the driver's vehicle, driving a vehicle, if you run off the road on your side of the road, run off road on the passenger side, head-on crashes if you lose control, but also head-on crashes if you're trying to overtake. These are 2 different crash mechanisms that are dealt with in the model. Crashes at intersections and crashes at property accesses. That might be where you know, a gas station maybe is connected to the road. That acts as like a mini intersection. So that's part of the model as well. The same set of crashes for motorcyclists, except it also considers the risk of motorcyclists being hit by vehicles as they both travel along the road. That might be a side swipe crash or a rear end crash, for example. For pedestrians, the risk is considered for people walking along the road, and that's whether they're on one side or the other, so it separates those out, but also crossing a main road, but also crossing a side road at an intersection. For bicyclists, the runoff road risk is considered intersections, bicyclists risk at intersections, and again, bicyclists riding along the road, similar to the motorcycle function. So they're the key crash types. And these crash types across those types and across those road users, they account for a really, really large percentage of all the road deaths that happen on the road. So it covers the crash pattern, whether it's in, for example, Thailand, where motorcycles account for, in many ways, a very high percentage of the deaths, right through a country where there's not much motorcycle or vulnerable road users, just cars, and through to situations where there might be many, many pedestrians. So it's very adaptable that way because it looks at these different crash types. The attributes that are recorded are listed here. I won't step through all of them, but there's about 50 different attributes that are recorded in an assessment every 100 meters along the road. So it includes, for example, whether there's a sidewalk, the number of traffic lanes, whether the road is curved or not, median type, pedestrian crossing, and so forth. So all of these attributes are ones that we know have some influence on either the likelihood of a crash happening or the severity of a crash when it does happen. A really important factor that I want to emphasize is speed. There's a really powerful factor in the iRAP model. And if you had a chance to use the star rating demonstrator in that assignment, if you had a chance to change the speeds in the model, you will have seen it has a huge impact on the star ratings. And that's because actually speed has a huge impact, not only on the likelihood of a crash happening, but the severity of the ones that do happen. This curve, or this chart that's shown on the screen, is one that's pretty typical. There's slightly different versions around the place, but generally what it shows is that at low speeds, or as you transition from lower speeds to higher speeds, the risk of death for different road users increases really quickly. And you can see on the left, the pedestrians are the most vulnerable. The 30-kilometre-hour point is really a tipping point for risk of death and serious injury for pedestrians. Once you have vehicles or impacts happening above 30 kilometers an hour, the risk of death starts to accelerate really quickly. So this is a really powerful factor in the iRAP model. For each of the attributes that are recorded, we also have what we call crash modification factors or risk factors. Now, these are factors that we put into the model based on the evidence that we've been able to find that's published in the literature worldwide. And what I'm showing on the chart is the risk factors for curvature. So the attribute that it's called curvature, it has 4 categories. So straight, a moderate curve, sharp curve, and very sharp curve. And what we've done is create these risk factors that are actually relative risk. So on the chart that you can see right now, where it says straight, you can see a number 1. That means we've set the relative risk factor to number 1. So all the other risk factors for different curves are set relative to that straight road. So the evidence tells us that as you get to a moderate curve, that's something about sort of 400 to 500 meter radius, the risk of death and serious injury, other things being equal, is about 2.2 times higher than on a straight road. As you get to a sharp curve, it's about 3.5 times higher than a straight road. And as you get to very sharp, it's about 6 times higher. The literature is obviously, there's many different studies that tell slightly different stories, but the risk factors that we've selected all the way through the model are our best effort to represent the real evidence about crash rates, the relationship between crash rates and these different road attributes. So this is one of the factors that's the set of factors that are used actually in the model. So the model then is it's comprised of different scores for the different road users and the different crash types. What you can see on the screen right now is, I guess, the equation structure that's used to calculate the pedestrian star rating scores. It's really small, so I'll explain a little. What's on the left is, in this green box, it says pedestrian star rating score. That is the sum, so that little plus sign there, of the scores for for pedestrians walking up either the driver's side or the passenger side of the road, for crossing the main road and crossing the side road. So it's the sum of scores there. Now, the along score is the product of factors that influence likelihood of a crash happening, factors that influence the severity of those crashes that do happen, operating speed factors, and what we call external flow influence factors. And I'll explain a few of those in a moment. But the factors that influence the likelihood of a pedestrian being hit by a car as they walk along the road are listed here. So it includes the sidewalk provision, whether the road is curved or not, the quality of the curve, sight distance, delineation, lane width, and so forth. Then the severity of the crash, if it does happen, is influenced by whether there's a sidewalk there or not. So what we do is multiply these factors together, these risk factors. They then form the likelihood, severity, and so forth. They get multiplied together to form a subscore for the along risk, and then they get put together in order to make the star rating score. So earlier I talked a little about the curvature risk factors, and you might remember Julio my colleague presented in the first webinar showing this same chart, which is the risk factors for pedestrians crossing a road or roads with different numbers of traffic lanes, so 1, 2, 3, 4 plus traffic lanes. So that's where that fits in right there into the risk of people crossing the road. That's where that set of risk factors fit in. So that's basically, in a nutshell, the structure of the equation that's used to calculate the risk score for a pedestrian at each 100 meters of road. So this equation is applied every single 100 meters along a road or a design in order to produce a star rating. So I won't go into too much detail with all of these, but this is the motorcyclist equation structure. I should just say in the link that I showed earlier, where it said irap.org/methodology, there's a fact sheet explaining all of these risk factors and all of these equations. So you can read these in more detail. So I won't spend too much time, but a similar structure is used for the motorcyclists. But remembering that those crash types, which are shown just to the right, of the motorcycle star rating box, are reflecting those crash types that I showed earlier in that table for motorcyclists. And the next chart is going to show the structure of the equation and an example of the risk factors for vehicle occupants. In this case, the chart on the right is showing the roadside object risk factors. So this is the risk of death and serious injury in a runoff road crash for vehicle occupants, and you can see on the right-hand side, a cliff gets the very highest score, whereas a safety barrier, a wire rope safety barrier, gets the very lowest score. So basically, the model is saying your risk of death and serious injury in running off a road on a cliff is 90, which is 10 times higher than if you hit a safety barrier, a wire rope safety barrier. And the next chart, I think, is going to show us the equation structure for the bicyclist. So as I said, I won't go into details of these, and you can review these in your PDF, but the structure is basically the same across all the road users, but the attributes and the crash types vary. I mentioned one of the elements in that structure equation was what we call external flow influence. So we had the factors that influence the likelihood, severity, operating speed, and then external flow influence. That's something that we've put together that's quite innovative, I think, in the way it's been used in the iRAP model. And this gives you an example about how the risk, or the distribution of risk, I guess, happens between runoff road crashes and head-on crashes on undivided roads. So on the image on the left, you can see the crash, I guess, the crash initiations that might happen on an undivided road if someone loses control and veers to the left or the right. So if they veer to the right, what might happen is they might recover. Maybe there's a paved shoulder that helps them to recover, or they might run off onto the side of the road. So that's the attributes that influence the likelihood of that happening would be in play. What they then hit on the side of the road is how it determines how severe the crash will be. If they lose control going to the left-hand side of the road and cross over the center line, again, there's a chance that they will recover. But if they don't, and there's a vehicle coming the other way, that runoff road crash actually turns into a head-on crash. So the object they hit is a vehicle coming the other way. So in a busy road where there's lots of traffic going in each direction, your chances of having a head-on crash are obviously higher because there's more cars coming along in the opposite direction. If there's no cars coming along in the opposite direction, like is shown on the little image on the right, then chances are that you have some risk that you'll run off across the road, across the other lane, and hit whatever is on the opposite side of the road. So the chart on the right is basically showing the distribution of, or the proportions of runoff versus head-on risk on an undivided road, depending on lane saturation. So it's basically saying as you get to a fully saturated lane where there's lots of traffic coming the opposite direction, if you have a runoff event to the left, you're basically guaranteed to have a head-on crash because there's cars there. But if you're on a very quiet road, your chances of having a head-on crash is very low. So it's perhaps a little complicated, and again, the methodology fact sheets explain this a little more, but that's one of the factors that are used in the model to try and account for the effect that traffic flows actually have on the risk of individual being killed or seriously injured. I won't go into detail here either, but I just wanted to highlight that in the methodology fact sheets, we have a worked example which goes through this photograph on the left. It provides some supporting data about the situation, so traffic flow, percentage of motorcyclists and bicyclists and so forth. And then it presents all the road attributes that are recorded, their categories and the corresponding risk factors, and how they're put together to produce the star rating scores. So in this case, the table on the right is showing the score for head-on crash loss of control, and it's giving you a score of 0.775. That alone, 0.775, doesn't mean a great deal, won't mean a great deal to you until you put it together with the other crash types for head-on, overtaking, intersection, run-off road, and so forth. So once you put those together, that's what goes together to compile the total star rating score. So in those methodology fact sheets, you can see a real example about how the calculation is done. And just to I guess emphasize, that calculation is quite extensive, is done every 100 meters along the road. So once we have those scores, once those scores in the equations that I showed are being calculated, then we simply assign those scores to a star rating band. And so just to take one example for the vehicle occupants and motorcyclists, if the score is between 0 and less than 2.5, that's going to be a 5-star situation. If the score is greater than 22.5, it's going to be a 1-star. So those scores that are compiled for the vehicle occupants and motorcyclists, bicyclists and pedestrians are put into this table, and that's how the star rating itself is produced. And of course, from that, then we get the metrics that are able to be produced in VIDA, which I recorded in the demonstration video. So on the left-hand side, what you can see is an example of the star rating, a star rating map for vehicle occupants, and you can see the color of the star ratings along the road changes every 100 meters or so. Yellow is a 4-star, orange is 3-star, and here we have a section that's 1-star. And you can also in VIDA see that in a chart form, where it actually plots the star rating scores along a chart. So in this chart, the bottom of the chart is showing the distance along the road from the start to the finish of the section of road. The vertical is showing the star rating scores. So the higher the score, the higher level of risk, and the colors in the background are showing the star ratings. So you can see that this chart corresponds with the color changes in the map, and you can see that 1-star section there is really showing the spike in the risk profile as well. And I think my last slide is that we've done quite a bit of research to put together relationships between star ratings and crash costs per vehicle kilometre traveled. So crash costs basically per traffic flow along a section of road. And you can see that there's this quite strong relationship where we can say, if you move from a 1-star road to a 2-star road, generally speaking, you might expect the crash costs per vehicle kilometre travelled to about halve. Then if you go to a 2 to 3, it about halves again, 3 to 4, halves again, 4 to 5, halves again. So you might have seen we often talk about trying to get roads to a 3-star or better rating. And this sort of chart really underpins some of the logic about that. You can really see that by the time you're getting to a 3-star road, the crash cost per vehicle kilometre travelled had really significantly reduced compared to a 1-star or a 2-star road. Of course, if you can get to a 4 or 5-star, things are getting very good. But by getting to a 3-star, you've really made a really significant reduction in that cost of trauma happening on the road. So that partly underpins why we've said 3 stars is a target to try and work towards. So Ali, I think that's the end of the presentation about the star rating methodology. But yeah, if there's any questions, happy to field them.
We have some questions. Thank you, Greg, for your presentation. A few people also commenting that they've watched the video on Schoology about VIDA, and it was very comprehensive. And also, we have one question here from John asking, surely the proactive approach assumes that the safety risk is universal, which is not necessarily true. So how relevant are the risk assumptions for low-income countries from Research Center on HICs?
Yeah, it's an excellent question. So yeah, I guess my understanding of the question is talking really about the relevance of the risk factors. So that chart that I showed, for example, with the curves where it said, okay, the risk of going from a straight road to a moderately curved road, the risk factor goes from 1 to 2.2. I think it's fair to say that like some of the risk factors might be slightly different in developing countries than others. That might be the case particularly for where there's really complex interactions of lots of vehicles and road users happening. But basically the model is based on the evidence that's published and the best that we could find around the world. And unfortunately, in many developing countries, this sort of risk factors are not yet really widely available. We are super keen to be able to bring those into the model as soon as we can. But I think what I suspect we would see is for many of the attributes, as we add new data and new evidence from more countries, I'm not sure that it would fundamentally change some of those risk factors. For example, I think the speed relationships are quite strong. They're based on they reflect people's tolerance to survive impacts. And in the end, people are the same all around the world. For example, I think also cases like a median safety barrier. If you put a median safety barrier into a road, it's going to be, generally speaking, very effective at reducing deaths in head-on crashes, providing the barriers, of course, is built well and maintained. So some of those factors might not change significantly as more data comes in, but absolutely, as countries develop their road crash databases and their research relating those road crashes to road designs, we should start to see more research evidence come through. And as that evidence comes through, we would really dearly love to be able to include that in the iRAP model. In fact, right now, we're doing a review of elements of the model to make sure that we're picking up the very latest research, particularly related to pedestrians.
Thank you, Greg. Just a couple of more questions. Is it so that the bicycle crossing is not considered in the star rating model? May it be at the intersection or mid-block?
Yeah,
I think
excellent.
it was the chart.
Yeah, excellent question. We don't have an attribute for a specific bicycle crossing. We have crossings for pedestrians, and I guess the assumption will be that bicyclists benefit from those pedestrian crossings. But yeah, at the moment we don't have an attribute specifically about the bicyclist crossings. So yeah, absolutely, that might be one that's considered for a future model update.
And also about the intersection, but the crash type at intersection may involve pedestrians. So improvement at the intersection are expected to improve the safety of pedestrian. Does the star rating consider the presence of pedestrian at the intersection?
Yeah, absolutely. So the crash types that the model considers for pedestrians are pedestrians crossing the road, whether that's across the main road or a side road at an intersection, or walking along the road. It doesn't sort of discriminate about whether that person is trying to cross the road at an intersection or anywhere else. They face a risk. So a pedestrian facility included in an intersection, like a pedestrian crossing, signalized crossing, that definitely is reflected in the model, absolutely. So yeah, pedestrians at intersections are definitely taken account of.
And I'll read another one. Why crash rates on curves don't take super evaluation into consideration? A moderate curve with no super evaluation can be more dangerous than a sharp curve with properly designed super evaluation.
Yeah, no, fantastic question, and it's absolutely true. One of the reasons that the way the model was developed is it's based on data collection in the field, and like we need to be able to the data that goes into the model needs to be able to be collected in a cost-effective way at like mass scale, and measuring the super elevation of a road in real time, it's a little challenging. It's much more challenging than the basic assessments that we do where we collect a video, and you can't really measure the super elevation from a video. So it's about the data collection, about the challenge of collecting data, more than us saying that it doesn't have an effect. It absolutely does have an effect, and I think it's important to say that the iRAP model, it doesn't capture everything that's possible in road safety. In the end, it's a model with a very well-defined list of attributes. But absolutely, there's things that happen in road design that are not really totally reflected in the iRAP model, and that's fine. It's not really possible to create a model that captures everything that can possibly happen. All that said, though, I think it would be interesting for us to think about how we bring super elevation into our assessments of designs. Because that is where the design specifies what the super elevation of a curve would be. So yeah, that's one that I think we can take on board and consider for the future as well, the design type of assessment.
Thanks, Greg. I think we can move on, and I will pass you all your questions to Greg, and we'll post the answers on Schoology. So we'll just move to the next presentations, and we'll have more time, maybe even to answer some of the questions fitting in the Morgan's and Marco's presentation. Thanks, Greg. And now I'll hand over to Morgan Fletcher, presenting Safer Roads and Investment Plan. Morgan,
thank you, Ali.
Presentation.
And thanks, Greg, also for the presentation of the star ratings. So if you move on to the next slide, Ali, I just wanted to give you a bit of a recap. You may have seen this slide on day one. I think Julio pulled this one up as part of his presentation. Just to show you where the Safer Road investment plan fits into the model. So Greg spoke at length about the structure of the equations to calculate the star rating scores. He also mentioned that the star rating score is the risk to the individual road user, whether that be a vehicle occupant or a pedestrian walking along the road or crossing the road, or a bicyclist or a motorcyclist. So in order to go from a star rating to recommendations of how we might improve the safety of that road, we need to do a few things. So first of all, we need to take the equation that Greg pulled up for the star rating score, which is the risk to the individual, and multiply it by the number of individuals of that road user group on the road. That gives us from that we can calculate a fatality estimate, which if you go into VITA and if you've seen Greg's video that he prepared, you'll see the fatality estimate there. We also need to really focus on the crash types that are happening on the road in the country that we're looking at in a certain project. So whereas star ratings are universal, a 5-star road is going to be the same whether it's in Ghana as whether it's in England. We really need to modify the Safer Roads investment plan to make sure we're targeting the problems and the crash types that are occurring on that road. So how do we do that? We calibrate the model to make sure that if we do have crash data available, that we calibrate the model to make sure that the fatality estimates are reflected or do match the actual crash types that are occurring on the model. Also worth noting here that the Safer Road Investment Plan is the last step in an iRAP project before we go into the implementation. So this is the last product that we can get out of VEDA before we start talking about the implementation, which really needs to be tailored to the needs of the client. So if we move on. So a Safer Roads Investment Plan shows a list of affordable and economically sound road safety treatments specifically tailored to reduce risk on the surveyed road network. Each countermeasure proposed in the SRIP is supported by strong evidence that, if implemented, will prevent deaths and serious injuries in a cost-effective way. Nevertheless, each countermeasure should be subject to additional prioritization, concept planning, and detailed design before implementation. There are 94 proven road safety options considered in the model in order to generate affordable and economically sound road improvements that will save lives. These improvements range from low-cost road markings and pedestrian refuges to higher cost upgrades, including intersection upgrades and full highway duplications. I think it's important to note that if treatments aren't right for local conditions, we can simply block them from the evaluation, so they're not considered at all, and they won't appear in the Safe Roads Investment Plan. So here we can see the process of how we come up with a SRIP, and the economic logic is basically as follows. So fatal and serious injuries are calculated for a baseline situation. Countermeasures are triggered, and a trigger, by a trigger I mean that a set of conditions that need to be met in order for a particular countermeasure to be considered by the model. A simple example here is if the road is coded by the person doing the coding is poor, then improved delineation may be triggered as a countermeasure, and depending on the next steps may be included in the SRIP. Fatal and serious injuries are reduced by the countermeasure, and this generates an economic benefit. So we're talking about the benefit here, and we also need to know the costs. So each countermeasure, when implemented on the road network, will have a cost associated with it. So both the cost and the benefit are calculated over a 20-year period using a discount rate. In order to compare the two, we need to know the present cost of the benefits to be able to compare with an upfront cost for implementation of a treatment. And if the ratio of the benefit to cost exceeds a BCR threshold, the countermeasure is recommended. Then a series of minimum spacings and minimum length rules are applied. For example, we're not going to recommend pedestrian bridges every 100 meters. We might need to look at a minimum spacing of 300 meters for that treatment. And finally, the model calculates a new or an after star rating and an FSI based on the selected countermeasures for each 100-meter segment. Sorry, I just need to plug in my computer. It's going to, before it does. I'm back. Next. So the steps of creating a SRIP, I've gone over them briefly, but we're going to go over them in a bit more detail here. So basically, we need to set up the economics. So how much would a countermeasure cost to implement, which is talking about the cost of that treatment, and what benefit in your economy could you expect to get from that? Then we need to customize the countermeasures, and we'll talk about that in a bit more detail. And finally, the calibration of the model. So making sure the fatality estimation reflects the behavior, vehicle fleet, and enforcement used on the network. So in order to define the benefit, there are two tried and tested methods. So the willingness to pay and the human capital lost output approach. So these two approaches are based on quite complex studies and they vary from country to country, and they're not readily available in many countries. So the SRIP uses a third method. It's based on a country's GDP, and it was developed off the back of research by the World Bank. So the default, and we can modify this if a country does have a different value that they'd like to use, but the default is 70 times the GDP of that country per capita. And while I called it the value of life, don't think of it the benefits as the value of life. You can't value life. Think of it more as a measure of what a country could afford to pay to save a life. We all know that there are limited resources in each country, and spending $1 on road safety means that $1 less can be spent on education or other things. So while obviously it'd be fantastic if we could achieve 5-star roads everywhere, there's also the balance that we need to achieve. So this is where the defining the benefit comes into play. So if we look at the setup in VITA here, this is a road that we've just a project that I'm showing here as an example from Kenya, and this is in the setup in VITA of that project. So this is where we define the benefit, and if you click on the next, we can see here that we've got a few defaults. For example, the analysis period for a typical project is 20 years. We assume a default of 12% for the discount rate. That's in order to compare the future benefits with current costs. We've got a minimum attractive rate of return there of 0.12. These are all defaults, but they can be edited. Moving down, we assume that the value of life of 70 times the GDP per capita, and we assume that for the cost of an injury, that's for the cost of a fatal accident, the cost of an injury is a quarter that. Some injuries are going to require very little treatment. It's very little in the way of hospitalizations and costs to a country, but some are going to be long-term injuries that require long-term treatments and have a really serious impact on that person's life. By default, we assume that there's, for every fatality on the road network, there's 10 serious injuries, and we suggest using a qualification criteria there of BCR and setting that to advanced. I won't get into detail on those ones because we've only got 10 minutes for this presentation. So moving forward, Ali. Sorry. So just having issues with the my power here. One second. Countermeasure costs. The investment plan requires countermeasure costs.
Hi, Morgan, can you see the slide?
Ali, perhaps I can step in while Morgan is obviously having technical problems. I think somehow this webinar series is a little doomed on the technology.
Yes, please.
Okay.
Thank you, Greg.
So as Morgan was saying, the countermeasure costs are one of the inputs that we put into the model. And this is a screenshot from VITA about how you set up a project. What you can see is you get to put in different countermeasure costs depending on whether it's a rural area or an urban area or a low, medium or high cost environment. So for example, putting in a safety barrier might be quite easy on a rural road where there's nothing in place, no trees, no other objects. But in an urban environment, putting a safety barrier in might be really challenging because you might have to remove some sort of objects that are in place. You can also put in the service life of each of the countermeasures that are considered in the analysis. So that's the life before that treatment expires. So here you can see the shoulder ceiling just at the moment set for a service life of 20 years. That means it might last for 20 years, but you can adjust that to 1, 2, 5, 10 years, whatever you like. So in the analysis, if you set it to 1 year, it's going to assume that you will need to replace that countermeasure every single year. So it basically picks up some sort of like a maintenance effect in the modeling. And as I was saying, so the countermeasure cost does change by the area type. So the two photographs show an example of a really dense urban area or a quiet rural area. Generally speaking, it's easier and cheaper to put countermeasures in the rural area than it is in the urban area. And like I was saying, also there's this option for the low, medium and upgrade costs. So if we take, for example, the idea of doing, let's say, adding a lane to a road, the photo on the left would be relatively easily. There's no real obstructions to putting an extra lane. Whereas the photo on the right, where there's a cliff, it would be incredibly expensive, so prohibitively expensive. And so, yeah, this gives you the flexibility to put in your range of costs that will affect the economic analysis that's happened. And you also then, throughout all of this, you get the chance to really customize all of those. So you can put in whatever cost you like. If you want to say use the same cost all the way through, doesn't matter whether it's low or high cost environment, you can do that. So it's completely, I guess, flexible about how you set up those inputs into your analysis. You can also turn off countermeasures in the analysis if you want to say, look, we never want to consider a zebra crossing in our analysis. We don't think that they're very effective. We will only consider raised pedestrian crossings. So you can switch off the basic pedestrian crossing from your analysis if you'd like to. And then also the calibration is a little complex, and this is something that Morgan touched on a little earlier. So although the star ratings are standardized across all the assessments, and Morgan, he said, like a star rating in one country, or if you have two roads, one is in Ghana, for example, and one is in Germany, if they are of the same design, they will pretty much get the same star rating. But what we actually expect is the numbers of deaths and serious injuries on those two roads might be different. And that relates to factors that go beyond the infrastructure design of the road. So to give you a simple example, let's say these two roads that we have, they're designed in exactly the same way, and so they get exactly the same star rating. And let's say we're considering vehicle occupant star ratings. In one country, though, everyone wears their seatbelts, and in the other country, no one wears their seatbelts. So other things being equal, although those roads have the same star rating, when crashes do happen, we would expect some more deaths to happen in the country where people do wear their seatbelts versus ones without seatbelts. So when we do the fatality estimations, there's a calibration that happens to reflect the actual numbers of deaths that are happening in a country. And that's a function of things that, like I said, go beyond the infrastructure element. And this is an example of one of the investment plans. So the outcome of all this analysis and data that Morgan has been talking about. And I talked about one of these in the demonstration video as well. So you'll have a good chance to see one of those live in that video if you click on that YouTube link. But just to talk through what you can see here, at the top of the table, you can see, or the picture, you can see a small table that begins with total FSIs saved. So that's fatalities and serious injuries saved. It says 3517, which is 3,517 fatalities and serious injuries saved over an analysis period of 20 years. So over on the right-hand side at the top, you can see 20 years. So what that's saying is if you installed all the countermeasures identified in the plan in the table below, you would expect to save that many deaths and serious injuries over 20 years. And that table is replicated for each one of those attributes. So you can see in the table bicycle lane, upgrade pedestrian crossing facility, traffic calming, the statistics about how many of those need to be installed, how many fatalities and serious injuries could be saved from each one of those countermeasures, and also the economic analysis in terms of estimated cost and economic benefit are listed there as well. So it becomes a really, really powerful tool for getting a sense of what you might do given a particular budget to improve safety of the road. And a really important point is that firstly, this can be produced for any budget. You could say, if I have $1,000, what would I do? If I had $100,000, what could you do? If I had $1 million, what could I do? So it can be really much tailored to the budget that you're working with. But also you should remember that it's a concept plan really. It's definitely not something you should take and say, okay, I'm going to install exactly 88.7 kilometers of bicycle lanes at the exact locations that the iRAP assessment said. It's just really a concept. What you really need to do is take this information, use it for strategic planning, use it for budget, shaping budgets, and use it as a guidance about how you might develop more detailed plans. But that will usually involve some sort of site visits to take this plan and say, all right, the bicycle lane here, it's going to work, but we need to do a little less or a little more, and we need to adjust how it would work. So it's really designed to get you started with something evidence-based and really constructive, but definitely it's very early in the process of a design and planning process. Oh, we're just taking an example, sorry, as these are Morgan's slides. So we're zooming in on street lighting. If you click again, Ali. So yeah, if we clicked in the map on street lighting, which is highlighted there, it's going to bring up a map which is shown on the right-hand side. Each blue dot shows where the street lighting has been suggested. So it's very, very detailed in terms of giving you a sense of where those treatments might be applied. But like I said, you would then go to each one of those blue dots and say, okay, is there really street lighting here or not? Is the street lighting improvement or installing street lighting functional and something that I should do or not? Looks like we have Morgan back as well.
Yeah, thanks for that, Greg. Thanks for covering. Sorry about that, everyone. Just some technical issues here that now seem to have been resolved. So jumping in, thanks, Greg. I'll jump back in now if that's okay. So just as Greg was mentioning, then quality reviewing the Safer Road Investment Plan is super important. And like all models, the quality of the data going in really affects the quality of the data of the results coming out. So there are a number of checks that can be made to ensure the model is run correctly and errors in the data are minimized. So while this is talking about the model in general, it really does have an impact on the quality of the investment, the countermeasures that are recommended in the investment plan. So checking things like the road condition data, section names, traffic volumes, and road attributes all have a huge impact on the countermeasures that are recommended. Costs, spacings, and land availability all play a big role in that one as well. And just I always when I'm looking at a road safety investment plan, I always do a kind of a sense check in relation to the countermeasures that are being recommended. Moving forward, and a good way, if we are looking at trying to make sense of a Safer Roads investment plan, is to compare it to the crash data that we have for a road network. If we do have crash data on a network, whether that be the risk score, as you'll find out in the next session from Marco, or simply looking at where we have conglomerations of accidents, we can compare that to the star rating scores. And you'll remember that Greg went into detail about the star rating score and how that relates to the star ratings through the bands. So where we have star rating scores that are extremely high, that means a high risk to the road users. We can compare that to where we have a high rate of risk on the road based on crash data. So that would be the blue box at the top. And that's where we have a very low star rating, 1 or 2 stars, and we have a high rate of accidents. So these locations are where we need to do investigations and take action immediately to improve the road infrastructure. Where you've got, for example, a high star rating score, so a very low star rating, and very few accidents. So it's identifying a problem with the infrastructure that maybe hasn't caused many accidents to date. That's where we can really take our time to engineer some improvements needed to prevent crashes occurring in the future. Where we've got in the green box on the y-axis, where we've got very high risk on the road network based on crashes, crash history, but we've got a very good star rating, a very low star rating score. There, we mightn't need to do too many treatments, but we need to look at road user behavior, enforcement perhaps, and really look at like the micro level to see what's going on and what's causing the accidents at that location. And finally, the orange box at the bottom left there, where we've got a very safe road in terms of the crash risk and also in terms of the star rating score. There we can do crash investigations for specific cluster sites and just really monitoring and make sure we don't need to do any major treatments there. So moving on. And just one of the final slides here. So the SRIP limitations. So as Greg was mentioning, it's not a bill of materials, the SRIP. It's really important to understand the limitations of the model. After all, it is a model. So I often find that the star ratings are really good for a project, and it's really good at identifying where issues are on the road network. But quite often, you need to use your engineering brain to make sure that the treatment that ends up being built on the road is the right one and not necessarily the same one as the solution that's being suggested in the SRIP. For example, you might find situations where the SRIP is suggesting that you remove an object on the side of the road, and you might, from experience and using your engineering knowledge, know that in that location it might be better to install a barrier or vice versa. So the model prioritizes road fatality risks that can be mitigated economically and suggests the types of countermeasures that would be appropriate. It doesn't make a considered engineering proposal. So it's really important that we go out and do site visits and make sure that the solution that we end up implementing is the correct one. So like it says there in the final paragraph, within each countermeasure in the SRIP, there's several ways that the engineering can be executed. Some of these could be inappropriate and counterproductive or expensive. So it's crucial that a more detailed audit and design is undertaken. And that's the end of my first presentation. So if there are any questions, I'd be happy to field them now.
Thanks, Morgan. We have a few questions, and also the first one asking if iRAP also include the specific cases like BRT or light rail or road metro. Sometimes when these are proposed, there are many safety issues in the design itself.
It's an excellent question, and we are moving a lot into the urban type analysis of road networks. So While we don't have specific categories and attributes for BRTs and things like that, we can model these in the assessment. So it is something that we can incorporate, but there's no specific countermeasures related to those. But a lot of the countermeasures that you do require around BRT stations, pedestrian facilities, and lower speeds and things like that are definitely things that are considered by the model.
Thank you. We have one question about the BCR. If you have a default BCR of 1 with all countermeasures not reaching that being ignored, how do you get a program BCR of 0?
So if I understand the question correctly, if we have a minimum BCR of 1, some of the treatments you might see are actually below that BCR of 1 in the actual SRIP. And it's a complex calculation that we do where we have multiple countermeasures. So I'll give you an example. If we have a road where we're recommending rumble strips on the side of the road and a shoulder and also a barrier, if we were to implement just one of those treatments, we might expect to save more lives for that treatment than if we implemented all 3 of them and we just look at that specific that treatment. For example, if we're just looking at rumble strips, if we were just to install rumble strips on the side of the road, we might save, for example, I'm just making up numbers here, but 2 lives over the course of 20 years. If we were to install rumble strips and a wide shoulder, we might save 3 lives. If we were to install shoulder rumble strips, a wide shoulder, and also a barrier, you might be able to save 5 lives. But the sum of all those 3 treatments is not going to be the same if we were just to install one of them. So that's where we can have a BCR below the cutoff that we've included in the BCR threshold there. I hope that answers the question.
Thanks, Morgan. We have a few more questions here also for the crash risk mapping. And I think you will come back with your final presentation. We can see if we'll cover more of them. Thanks. Thank you very much for your presentation. And now I will introduce Marko Sevrovic, presenting the crash risk mapping. Marko.
Thank you, Ale. Yes, so in this presentation, I will speak about the protocol called the crash risk mapping. So we spoke earlier about the difference between the reactive and proactive approach, and the focus of this presentation is actually one of the protocol that iRAP has, which is a reactive protocol. So meaning that it's based on historical crash data analysis. So basically, in order to be able to produce a risk mapping, you need to have data about accidents that happened on your network in the past period, whether it's 3 years or 5 years, or if you have more than 5 years, that can also be used. And it's kind of similar to the traditional approach to road safety, where we used to do a detailed crash analysis, where we used to do the hotspot analysis, coming from the theoretical concept developed in the 70s, showing that around 50% of fatal accidents, fatal injuries actually happen on less than 10% of the network. So this was the guidelines where the reactive approach worked well in early stages of road safety. But then again, as I mentioned in my slides with the balcony, there's also a link, a scientific link, that there is that we actually know which locations on the roads are dangerous. So that's why we are using the proactive approach as well. So basically, as Morgan was saying, the combination of the two approaches is what gives you the right overview. So we'll speak about that a little bit on the next slide. So Yeah, basically the iRAP crash risk mapping is a set of maps. It's a set of color-coded maps that are displaying, very visually displaying the risk that is there for the individual road user or the community as a whole. So there are different types of maps, which I will be speaking on later, which are then color-coded in a very visual fashion, so that you can actually see road sections which are riskier than other sections in terms of the number of crashes that occurred, and also taking into account the ADT, or the annual average daily traffics and volumes which are occurring on those roads. And the thing is that this protocol is also based on the methodology that can be compared. So you can easily compare maps which are created in different countries based on the road data, so that you can actually see what is the risk represented in one country compared to the other country. And this is usually used in Europe, and many people are actually publishing those maps even for the public, so that they can have the communication, they can understand that the roads that they are using, if they are taking a trip, they can select a route which is less riskier than the other. And also you can use those maps to compare what is the trend of your road safety in the country. So you can compare the maps from different periods. Morgan will be speaking about this later on in his presentation, so that you can see how your traffic and road safety performance is actually being developed through the period of different years. Next slide. So the methodology itself follows a process. So first, what we have to do, we have to define the data sources, and we have to define the network that we want to cover with our map. Usually this is a crucial part of the process, because there is always a problem with the availability of the data and our expectations. So generally we would like to have risk maps for the whole road network of a country, but usually it's not that easy to collect the data for a vast network. So a typically good approach would be to start small, to only start producing a risk map of your main routes, main travel routes, main transit routes, and then just build from that and develop your map accordingly. And to do that, you need to collect the data, you need to collate the data about accidents, about traffic volumes, about geometric features of your road, and then you do a process very similar as in transport modeling. You need to assign this data to the actual features in any GIS system or a table, so that you have the data collated in one location, so you can calculate the risk based on the formulas. After that, you come to the process of producing the maps, which is a standard process using the GIS tools. And of course, as in previous iRAP protocols, there is always this important part of the quality review. And then if you want, you can also publish the results or use it internally. And this usually requires these two main focuses, which is including testing and sampling of the data, and defining who is the audience that you actually want to publish the data for, and also the talking with the road authorities, so that they understand that this data is not really, that those maps are not there to say that the roads are not good. They're actually there to just pinpoint the problems on the network and the locations where investment should be done in the future. Next slide. Yeah. As in all iRAP protocols, there is a very good guidelines or a set of documents that actually explain and define how the protocol should be conducted or undertaken in a country. So there is this technical specification that defines the standardized approach for benchmarking between countries, that defines the risk mapping principles, how you should handle the data, how you should define the network, how you should calculate the risk. Typically, if we would have more time in this presentation, we would go through all of those formula and explain how it works, and then you would be able to calculate data by yourself. But again, this document is available on the iRAP website, so if you want to know more, you can always go there and check on how to actually produce the map yourself. Next slide. Coming back to the steps, to the necessary steps, as I mentioned earlier, the important part of this is to have information about the fatal and serious accidents happening over time and with known locations. Of course, this is a challenging thing. So in many countries, we have different sources of problems. Either we have the numbers, we know how many people have died or have been seriously injured, with a consideration that there might be some underreporting, so that some of the accidents were not reported, and the definitions of a fatal and serious injuries differ from a country to a country, and usually this data is available with the police or with the road authorities or even insurance companies in some countries. The accuracy is not always the same, and the typical problem is the locations. So sometimes we know the numbers, but we don't know the location. So actually getting this data into the readable and usable format is the biggest challenge of performing this protocol in general. But of course, also annual average daily traffic is important, because as we said, we are calculating both individual and collective risk. So we need to know how many accidents are actually happening in terms of the billion vehicle kilometers traveled on a section of a road. So knowing all those information is crucial to having correct data. But as you know, annual average daily traffic can also be estimated. So if you have traffic counts which are only point counts, and if you have a distribution, or if you have just a small surveys, 15-minute counts, you can with pretty high accuracy calculate the annual average daily traffic on some locations, and that can easily be used to perform the crash risk mapping. And the length of the road, of course, is calculated from the geometry in the GIS system. Next slide. And with on the iRAP website, this protocol has its own template. So there is an Excel template that you can download that is basically an Excel table with all of the formulas already in, where you can insert and input the information about your desired network, meaning that you put in the first GPS point, the end GPS point of a section, enter the name of the section, and then enter the data about road traffic accidents across the year span of the period that you are actually observing. And also you can add some more information like carriageway type, junction type, type of accidents, so that you actually get a more detailed analysis for the purposes of star rating and combining the risk mapping and star rating for the investment planning. Next slide. The road link aggregation itself. So we used to have a lot of questions coming in, so from the new users of this protocol on how they should actually aggregate the links. So the purpose of this map is not to pinpoint a particular location on the map, but it's to define the safety across a section. So a typical section of the star rating and risk mapping in this protocol would be around 5 to 10 kilometers. So you actually collate all the data which is available on few smaller sections into one larger section, so you can actually represent it on the map. And what you are usually doing, you are only combining the roads which are in the same class. So we don't combine motorways with single carriageways, we don't combine urban roads with rural roads, so it's usually aggregated in a way that a type of a road represents a section which has the length between 5 and 15 kilometers, depending again on the network of a country that is available. Next slide. And as mentioned earlier, the maps actually show us the individual road user risk present on the network, but it also shows the community risk as a whole in a country. And those maps can also be used to reflect the national policy targets. So for example, you could define a map like this and identify all the high risk sections of your roads, and then set a national target saying that in the next 10 years we want to eliminate all the high risk sections on the network. And this is a traditional approach that has been used in many countries, and combining that all together with the other protocols from iRAP, you can actually prioritize investment based on facts and the actual savings that can be produced by implementing road safety countermeasures on the network. Also, those maps can be used to pinpoint the road types which are more dangerous than the others. So usually when you look at the map of a country, you immediately see that motorways are generally in a low or medium-low levels, and single carriageways, rural roads or urban roads are usually in a high-risk category. So pinpointing that can also lead to the conclusions where you have to invest and what design of the road should be changed or should be improved in the future when you are designing the new type of roads and considering the development of new roads in a region. And also those maps can show you where any changes in the layout, actually building a second carriageway could actually improve the road safety situation quite a lot. Next slide. And now coming back to the map types. So I mentioned that there are 4 main map types, and there is also additional map type. We call it the map type 5. When the first map type is actually the risk rate expressed as fatal and serious injury crashes per billion vehicle kilometers traveled, meaning that you actually multiply the length, you multiply the ADT, and then you divide it all by the number of crashes that happened on the road section, and that way you get the distribution of the risk across the billion vehicle kilometers traveled. Of course, a road that carries 100,000 vehicles and has 10 crashes is less dangerous than a road that carries 50,000 kilometers and has 10 crashes. If you have more vehicles and the same number of crashes, the risk is of course lower on a road that has more vehicles. And of course, if the length is longer, then also this risk is reduced. Also, the map type 2 shows the risk rate expressed as the number of fatal and serious injury crashes per kilometer per year. This is the density. So we basically can see if there is a clustering of, if there is a problem of the road. And this is typically used by road authorities because they want to, of course, assess the priorities in a way that they want to improve the roads where they have the most crashes. So all of those map types have different uses. And of course, they are not the same, which will be shown on the next slide. If you're speaking about the risk map in type 3, so in the risk map type 3, Ali, if you can please go back just as the next slide in my, yeah, sorry. In this, we have the crash per billion vehicle kilometers relative to the average rate of roads with a similar traffic. What does it mean? So, for example, if you have a network of motorways, you can average the crash rate for a motorway, and then you can check whether a part of the motorway is actually below or above a certain threshold that you set for the average. This is usually good in areas where you have different types of networks. So sometimes if you compare the whole network together, what might happen that you don't identify sections of motorways that carry greater risk than other sections. So that's why we produce maps which are based only on one road type. And finally, risk map type 4 is also showing the sections where we can have the above average savings in crashes that can occur, which are linked to the infrastructure and to the type of the road. And the additional map is also can be produced that shows the cost of the accidents that are actually happening on the network, and this map is also quite useful for the investment decision making. Next slide. And just on the next slide, you can just see the illustration how the same network in UK shows different coloring based on the type of map that we are actually using. And you can also notice that there are some small bits and pieces which are in the same category of high risk in all 4 types of maps. So meaning that those are the roads which are a problem and that have to be attended to as a priority. And of course, combining this with other iRAP protocols gives you the information of the prioritization of the investment. Next slide. An example, how does it typically look? This is a map recently produced in Greece, where you can see that they covered a network of 4,323 kilometers, where you have the distribution of only 1% of the road network being in low risk, and then 23 being in low medium risk, 20 in medium risk, and 35 and 21 respectively being in medium high risk and high risk roads. Meaning that if you are also having this map, so you can now clearly see which roads you should attend to first. So typically those roads and those sections used in risk mapping are a little bit longer than what is usually considered for star rating, but not necessarily. But if you are planning to do a small scale survey, it is easy to do a map like that and then target the additional road surveys based on the map like this. So for example, you can see on the map the roads which are in the high risk. So the next step would be, of course, to attend to those roads and do a more detailed analysis, whether it would be star rating or road safety inspection on road safety audit or anything else on those locations first, if you want to prioritize inspections and safety assessments. Next slide. Speaking about the combination, I think, Ali, there is another animation here, so next. Yeah, so it is important to state that the road safety measures only reduce crashes if they are matched to the existing risk. So that's why somebody asked a really good question, saying that if you want to invest in a particular part of the road, as we mentioned in our example with the balconies, we are not rich enough to invest in all roads. So that's why it is very, very important to use all of the protocols available so that you can actually reduce the actual crashes. So if you invest in a road, you have to make sure that your investment is on the location where the crash will happen or have been happening historically. So that's why it's a little bit tricky. It's not always easy, but this is the way of doing it. So although we try to move away from the reactive approach to the proactive approach, we still need the reactive approach so that we can target investment in the future. Next slide. And just to show you how star rating and risk mapping actually correlate. This is a graph from the SLEAM project, which was done in 4 European countries this year, showing that you can see the correlation. This is the mathematical formula and the mathematical curve showing the link between the star rating and the risk mapping. So you see the roads which are risk mapped with a high risk. So the highest level of risk identified was 131.9 on the left-hand side of the graph. You see that it actually corresponds to the 1-star road in star rating. So not all roads are actually fully correlated, but the general correlation, which is shown on this graph, actually shows that in many countries there is a clear link between high risk sections defined by risk mapping and the star rating. So meaning that the infrastructure is not really good on those roads and the protection for the end user is not really correct. So by combining the two together, we can actually target the left side of this curve and to get the highest benefit with our investments that we have available for a particular road section. Setting priorities, here we have a map of, this is a risk mapping of a major road network in Bosnia. And then on the next slide, we have the star rating. So, and as you can see here, there is much more one-star sections than the risk mapping. And this is the combined map where you have the link between the sections that have a very low star rating and a very high risk rating. So those roads stated here are critical, and they are suggested for the improvement to the national government. And that would be my last slide. Sorry for taking a little bit more time than expected. So if there are any questions, I'm here to answer it.
Thanks, Marco. Very interesting presentation. Thanks for your slides and presenting. We are out of time. We have a few questions for you. I will send to you, and then we can post the answers on Schoology. Okay? And then we can move, because I will ask everyone another 10 minutes maybe, because we have one more presentation, very interesting, that will wrap up the information about iRAP model with Morgan Fletcher presenting tracking performance over time.
Thanks, Ali. Just being aware of the time, I'll try and get through this one a bit quicker. You've already seen these two, next slide, please. These two targets that Greg spoke about, the UN road safety targets, which is in support of the Sustainable Development Goals. So just a bit of a context as to why tracking performance is important. In order to try and achieve these goals, we really need to know where we are and how we're going to achieve them. So it's really good to be able to use the iRAP methodology as a benchmark to see how we're going and really have those two targets in mind when we're making any decisions about road safety going forward. So in saying that, I'm going to give a few examples of where we've done some performance tracking in different parts of the world. So if you can move on to the next slide. So the monitoring and evaluation of the effects of road safety upgrades on road user risk and the number of fatal and serious injury crashes, it's just really important in order to assess the effectiveness, improving our understanding of the types of treatments that work in certain locations and the environments, allowing funding agencies and road authorities to track performance. So you can see here, I've got an example of the risk mapping and the performance tracking from one period to the next. So the performance tracking, it's not just related to risk mapping or star rating. We can use either of these two approaches or methodologies in order to do risk mapping. So moving on to the next slide. And the star rating, sorry, the risk maps have been a really powerful tool to do this throughout Europe. So across Europe, across the UK in this example, there are a number of different risk maps looking at the performance over time, where certain roads have improved in terms of the crashes, number of crashes, where they've gotten worse. And it's a really useful tool is to try and understand why these changes are happening on the network, whether it's through user behavior or changes to the infrastructure itself. Next slide. So we can again use performance tracking of the star ratings. So if you click on the next one there, this was a demonstration corridor in Karnataka, India, where we went from a 1-star road with a huge number of fatalities and serious injuries on the network. In the left-hand example there was a skewed angled intersection and no traffic calming. On the back of an iRAP assessment, the intersection was upgraded and it went from 1 star for pedestrians, 2-star for the other user groups, to 3-star for all user groups there. And in the years since, there's been a reduction in of 27 deaths and 124 serious injuries on average per year. And these reductions, was really interesting, is that they matched the iRAP forecast at that location. Next slide. In my part of the world here in Latin America and the Caribbean, another demonstration corridor project where on the back of an iRAP assessment, a number of low-cost treatments, shoulder widening and things like that, improving, removing some of the roadside hazards. Some works of this type were implemented, and it's worth noting there the difference between the pre-existing fatalities to what happened afterwards. So we went on this demonstration corridor from about 50% of all fatalities in Belize occurred on this one corridor. After the iRAP assessment was undertaken and the road was upgraded, we went down to about 10% of the fatalities. So from 33 fatalities in 1 year in 2009 down to an average of less than 10 after the upgrades. And this also was based on an improvement in the star rating as well. Moving forward. Another example here from the Philippines, where Greg was involved in this one. So in 2016, an assessment was done. We found that for vehicle occupants, we had a 2-star road on the baseline, and for motorcyclists, it was a 1-star road. A number of changes were made, quite low cost, curve marking, street lighting, and safety barriers, and then that improved the condition of that road to a 3-star for the 2 key user groups there, which were vehicle occupants and motorcyclists. Next slide. In Bogota, Colombia, another project. This one was actually linked to the Bloomberg Big RS initiative. So the safety of vulnerable road users was a really high priority for the city. So in 2017, the city worked with Bloomberg and the Global Road Safety Facility, and obviously the World Bank to upgrade 2.7 kilometers on Calle 80 in order to provide a safe route for cyclists. And they achieved a 5-star rating for that user group. And we saw a really strong support from the local communities when these projects were implemented. Next slide. So this is getting into the African region. So in Addis Ababa, in Ethiopia. So some of the treatments here that were looked at between assessments in 2016 up to 2018. So the roadsides and markings were improved for about 75 kilometers. There was about 3,500 street lights that were installed, all focused on pedestrian and vulnerable road user safety here. And 2.6 kilometers of guardrails were maintained and installed. And speed management was also a big focus of this upgrade. So there was a review of the legal speed limits. The TMA installed speed limit signs at about 135 kilometers of main roads. Arterial roads were signposted at 50 kilometers and collector roads at 40 kilometers. And local roads with high pedestrian activity, which is really important here, were signposted at 30 kilometers an hour. And we can see there from the before and after, there's an improvement in the star rating for these roads as well. Moving on. And in Accra and Ghana, the La Paz intersection on N1 highway. So in 2015, a person died basically every fortnight on average at this intersection. So every day pedestrians took huge risks. You can see on the left-hand side trying to cross this road, where they had to cross 14 lanes of traffic mixing with heavy vehicles and with cars traveling at speeds of around 90 to 120 kilometers an hour. So as part of the Big RS project, so the partners in the Accra Metropolitan Assembly worked together to change the situation there, particularly for vulnerable road users. And we saw an improvement from, you can see on the left-hand side there, a 1-star road for pedestrians. And looking on the photo in the middle there, that was improved to a 4-star road for pedestrians. And so the work's also included increasing signal timings from 18 to 24 seconds to allow pedestrians more time to cross, lowering curbs to assist the physically challenged, narrowing lane widths and widening median refuges, all real pedestrian and vulnerable road user focused treatments there. And also some for cars, so replacing crash barriers and remarking the pavements. And if you move on to the next slide. And that's it from me. So I'm not sure if we still have time for questions, Ali, or if you want to address those via email later on.
Yes, I think we will post the answers to many questions that we received during the webinar on Schoology. Many thanks, Morgan, for your presentations. I think we can wrap up now. And if you, again, please make sure you access the course on Schoology. There we'll post this presentation, the video, and the answers to your questions. We have a welcome chat there. You can talk to each other. We've seen many people meeting and greeting each other, which is very interesting. And you can also post more questions if you still have some questions for the presenters. This course will be open until the 30th of July. And you can submit your assignments until this date. There is no timing for assignment 2 or 3. You can post and submit until this date there, and we will issue certificate after you complete all the activities. And our next session will be on Friday. We'll talk about case studies and establishing a RAP. We'll have more case studies for Africa as well. Rachel will present that, and Julio will explain how to develop a locally owned and led RAP in your country. Some of you already asked about it. Luke Rogers will present how to plan and procure an iRAP assessment with accredited suppliers, and I will present the training, the iRAP training and accreditation, and I will also announce an opportunity for low and lower middle income countries in Africa for training and accreditation. So don't miss that session. It will be very important for you to know. And we'll also talk about your assignments. So again, please, your feedback is very important for us. Please stay on the line, and there will be a feedback form for you to do an evaluation about this session. And to end our session today, apologies for the time, but I think the presentations were very good and important to know more about the iRAP model. Thanks for attending our third session of the World Bank and iRAP Helping Save Lives in Africa, BRS 2020-25 webinar series. Thanks for your participation. Thanks for the many questions we had. And thanks to our presenters. Do you want to say your final words for today?
I'm happy to begin. So yeah, thank you everyone for joining. Thank you for staying on for quite a technical and long webinar. And I hope you learned a lot, and looking forward to hearing and answering all your questions.
Yeah, just to reiterate what Greg said, thanks a lot for joining us and sticking in till the end. Apologies for the technical issues that I had during my presentation, but thanks to you too, Greg, for covering for me. Thank you.
Yeah, from my side also, a really big thanks to all of you dedicated to road safety, and I hope that we boosted your enthusiasm a little bit with those presentations. And if you need anything from us, we are always here to help you, and so that you can do your very important work in your country.
Thanks, and see you all on Friday for our last webinar